Hi everyone. So we are Friday today, and this is the first session of the paper's video recording live session. This is the first one of the year and of this new season. So actually, I'm speaking in English today. It will change a little bit than usual, and the idea is to read some papers talking about Erlang. And for the first one, I wanted to read one of the first publications made by Joe Armstrong in 1989. So just for the history, Joe Armstrong started to work on Erlang in 1985 or 86, something like that. It depends. And I think this is the first papers we have currently explaining a little bit what was the origin of Erlang. So this paper, I found it in July or maybe August, and it was kind of hard to have it directly in PDF, so I took it directly from archive.org. Sorry for the low quality, this is just a screenshot from my browser. So, anyway, this paper was published on the software engineering for telecommunication switching systems. As I said previously in 89, sorry. And actually, I don't have a lot of information about these things, so I don't know how to organize this session. I think I will read it and will probably ask some question. And if I have time, I will take a look directly on the web to try to understand the reason why, how it's working and what kind of constraints Joe had during this time and this period. I have also the Discord channel on the left side, so if someone want to ask question or if you have something to say, just do it. I think perhaps we will have some discussion after that. Anyway, I will start. So, the title of this paper is Using Prolog for Rapid Prototyping of Telecommunication Systems. And the authors are Joe Louis Armstrong and Mike C. Williams. I think those are the main original author of Erlang. And these documents have been created at Elmtel Utvedlings in Sweden. So if you want to check it, we will check if it's. Oh, sorry, just one second. Okay, so I think it's Elmtel Ulvelglings with my beautiful Danish accent or Swedish accent. So okay, this is in Swedish. Telecom AB for. Okay, do we have it in English? No. Okay, it's interesting. It looks like it's still relevant today, and this company is still existing, but I'm not sure. Oh yeah. So weird. Not know, we'll check that after. So, here's the introduction. The theme of this paper is to use Prolog for the rapid prototyping of telecommunication systems. Rapid prototyping techniques can be used for the incremental system design of large systems and for the tools required to build them, instead of designing the complete system and then going into an NC implementation of test files. The various components of the system can be prototyped and tested within a very short time. In this manner, costly fault in the system design are isolated, and at an early stage in a project, an experiments with alternative implementation techniques can be performed before being committed to particular technology. So this part is really interesting because this is what we have even today with continuous integration and continuous development stuff. The idea is to create some prototype, modifying them and deploying them, testing them, and so on. Earlier work concentrated on the advantages and disadvantages of various styles of programming: procedural, declarative, object-oriented, etc. The work described in these papers build upon some of the conclusion of three, and in particular addresses the problem of a language for prototyping telephony software. So I will just take a look on the 2, 3, and 1 paper just at the end. So the first one is a CS programming Prolog. So this is a book, I guess. Second one, experiment with programming language and techniques for communication application. It has been published in 1986. And the second one, oh, this is another really old one, 1986. This one, okay, so I will just take a look on it and I will probably read it the next time. The following philosophers problem or logic programming for telecommunication application. Okay, so let's take a look on that. Okay, I don't even know if it okay, I don't find it, so it's perhaps maybe the reason why I don't have it in my list. I think I will take a look later, but that's quite interesting because in 1986 I think Erlang was already in the pipes, and so a paper was created at this time. And the second one, oh no, this is this one, sorry. Okay, that's good to know. Let's continue to read this paper. The remainder of this paper discusses our implementation of a prototyping language, our prototyping environment, and our experiences of using this environment. Okay. So let's start the main topic of these papers, the language development cycle. We started this work with the desire to create a uniform framework in which we could perform experiments with different styles of programming and system architectures. This part is really important, in particular the uniform framework. I think like 2 or 3 months ago I was talking with someone who wanted to create a kind of universal something, universal connection to something, universal thing, and it's really interesting to have this word uniform framework. I think Erlang is about universality and about creating something that could be easily plugged to other system, and that yeah, I think it's interesting with different style of programming and system architectures. In order to test our ideas about programming, we envisaged the following iterative loop: ideas about language, prototype interpreter for language, test programs written in language, verification of test programs on telephony hardware. All the steps in this cycle are equally important. In order to test that language, IDs are correct, we need to build an interpreter for that language, write programs in the language, and test those programs on some telecommunication hardware. If we do not take these steps, then we will never really be sure that our ideas are correct. I think this paragraph is also really important for many reasons, because Joe and Mike are saying there that we need to have something to test it to break. We need to break stuff to move forward and to have new solution about our problem. It is important that we can quickly iterate through all the steps in the loop. We would like a cycle times of days such that language IDs can be tested on the hardware within a few days of their conception. Again, this paragraph and the next one, the previous one, are really, really important. And that's really nice because this paper is from 1989 and they are talking about something we're actually dealing with even today. That's really, really interesting. Languages. When describing telephony, a succinct and powerful notation is one of the prerequisites for producing high-quality software. If the notation does not allow clear statement of the problem, then unclear programs will be the result. It is very important that programmers are allowed to say exactly what they mean and not have to resort to clever tricks to express themselves. This paragraph is also totally insane. So what does it mean? It means if you want to write something down, if you want to write your program with some kind of language, it must be clear and understood by everyone and everybody. It's really important because we need clear statements. If we don't have clear statements, we can produce unclear programs. That's a good summary. We also believe that programs should be as declarative as possible. Yeah, that I don't remember the name for that in English, even in French, actually. How to say that? Okay, not in French, in English, sorry. It est. That is, okay. That is, it's the same as in French, but I was not sure. That is, that they should express what is to be done at any particular time, but not how the operation is to be performed. That's also interesting because we don't want to know how the operation is made. We just want to know what it will be done. This is quite a big difference. If we are creating something with the O, we will need to do some procedures, a long list of procedure. But if we have a what, this is a more abstract way of doing something. Having invented a particular language for describing telephony, the next step is to parse the external notation into some abstract form and then write an interpreter for the abstract form so that experiments can be performed using the language. Okay. The interpreter can be used to run program in the language, perform experiment with different architectures, and perform experiment with the hardware. And I just want to check something, just 1 second, because I have some issue with the sound, just to be sure it's working correctly. Okay, it looks good, so I will continue. I just want to do something because actually I would like to put some music there. Because okay, the interpreter can be used to run program, blah blah blah. Okay, once such a cycle has been established, it then becomes a simple matter to introduce changes to the original language and to quickly propagate changes in the language through the parser, interpreter, and into the runtime system. The entire cycle can be made so fast that the individual steps lose their significance and the system appears to undergo continuous evolution. When this process finally converges, the result is a design for a particular language. That's the first time I read this paper, and it's amazing. It's awesome. It's crazy. How long? The previous section outlined the prototyping approach on the main development cycle. In our laboratory, we have established such a prototyping cycle. The system is based on the Sixtus Prolog and has been used to drive a variety of different telephony hardware. Okay, let's check. Sixtus Prolog. So, yeah, it's still available even today. Okay. Start page, documentation, download. I want to try that. Okay. Put it in download. Okay. Is it working or not? I don't know. Just a readme. Okay, I need a license. Unfortunately. Is there a price somewhere? I will check that later, but I think it would be nice to have it to execute the different code. So, this system has been used in the development of a language to which we have given the working name Erlang. So Erlang is from the name of the mathematician Agner Kraprup Erlang, was the mathematician who developed the theory of stochastic processes in statistical equilibrium that is widely used in the telecommunication industry, and the prototype operating system for running Erlang program. So this is not Ericsson language. We have the proof here. This is from the name of Agner Erlang, the mathematician. That's crazy. Erlang started as an attempt to model telephony processes using formal grammar. It soon became apparent that the specification of telephony involved far more than a purely grammatical approach to the problem. In telephony programming, there are certain domain-specific design features that must be reflected in the language. Some of the characteristics of Erlang are: it looks like a single assignment functional language. Function selection is through pattern matching as in a logic language. Modules are used as an aid for structuring large program systems. Concurrency support is provided for processes, process management, and communication. Message reception semantics are similar to SGL. This simplifies the task of turning an SGL specification into an Erlang program. Error recovery mechanisms are inbuilt. So SGL Z100. Okay. I really don't know what to. Oh, that's a telecommunication standard. Okay, so actually, one of the requirements from Erlang is to be compatible to SGL, and SGL is kind of standard way to write something in the telecommunication area. Okay. So this list is by no means complete, but highlights some of the principal language design features. In addition to purely language features, we must also be concerned with various implementation issues. For example, granularity of computation. Telephony applications program must handle thousands of simultaneous transactions. If we assume that each transaction is modeled by a collection of processes, then we want the system overhead in creating or destroying one of these processes to be very small. So first, the word transaction is really important. When I read one book, I don't remember the name correctly, but I think it's computational transaction. It's gray journal book. I don't remember the correct name. Okay, this one here, and this one is a really nice book, and it was written by Jim Gray. And the first time I read it, it was like 5 years ago. So I was already doing some Erlang stuff on my side. But each time I was reading a part of this book, it was like it's really similar than Erlang. And in this book, if you have time to read it or buy it, I think it's quite expensive, like $60 or something like that. It's quite expensive, but it's really interesting. When you read it, every chapters will describe some transaction model, and at the end of every chapters, you will have a kind of feeling that this book is describing, it is a description of Erlang. That's crazy. So you should read it definitively. So sequencing of side effects. Telephony programs spend a lot of time controlling hardware. Controlling hardware is viewed as a side effect, and all side effects must be strictly sequenced. While the behavior of any particular hardware unit can be modeled as a sequential process, many different hardware units simultaneously perform different actions. So we need to be able to express both sequentiality within a process and concurrency between different processes. Time plays an important role in real-time application. Handling of timeouts and time-critical activities must be built into the language at a low level. Distribution should be hidden from the application programmer. The same program should run with minimal modification on a variety of different processor architectures: uniprocessor, shared memory, multiprocessor, and so on. That's interesting. In particular, the sequences of side effects. When someone asks me what's the difference between, for example, Erlang and Haskell, I always answer, something like Erlang is putting all side effects in isolated processes, and Haskell is doing all those side effects in monads, but one is probably more flexible than the other one. When you are putting in a process, the process just die and we don't care anymore. But the concurrency is directly inside the process and outside of it. I'm not sure if it's really the case with monads, and it's also perhaps why I prefer Erlang for concurrency programming and distributed programming. So, Erlang example. In the space available, we can do no more than give some short examples that show the flavor of our language. Our first example describes the startup phase of POTS. This code is taken from a larger POTS program which runs on our prototype, where it is used to control a small PIBX. The full prototype exhibits a much greater range of telephony features. So PIBX, this is telecom devices, to deal with the different call from one users and other user. All subscribers start in a state called idle. More formally, which rule says that all the control process that control subscriber devices start by evaluating the function idle. The syntax is quite similar than the one we have today, except, for example, the question mark here and the arrow. But oh no, this is the same. We can also send messages directly to a process. Start ringing B, other, ignore anything else, dot self, and we loop. Outgoing call, okay. From the idle state, subscribers can go off hook and start an outgoing call or they can accept a call request, in which case an incoming call is started. In the case of an incoming call, a ring signal is applied to the telephone set, and the system enters a state ringing B. All other events are ignored. The syntax proc exclamation mark mess means send the message mess to the process proc, and the syntax receive proc blah 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 means try to receive message 1 from proc run. Process name can be variables or constant. Messages can be arbitrary data structures containing variables and constants. Any variables in the process names or message descriptors are matched against the entries in the message input queues for individual processes. If a match occurs, then the appropriate variable in the process or message data structure are assigned values, and the matching message is dequeued from the process input buffer. Assuming we have an outgoing call, the code continues as follows. Okay, so we have the description of the step, I guess. Oh no, outgoing call. Okay, so this one is this one here. Wait first. Okay, this one will go there. Wait clear. Wait clear. We don't have it. Idle, come back to idle. Save digit. Okay. Note that timeouts were introduced with the syntax receive timeouts code. Yeah, okay. This causes code to be executed if no other acceptable message has been received within the time. Written in such a style, pods can be written using certain functions, of which we have seen 3. The total system including number analysis, switch manipulation, and the with a pair call error recovery mechanism can be written using 63 functions. We now turn our attention to the problem of number analysis. We wish to construct a function lookup that analyzes some number sequence sec with respect to an analysis struct and returns a vacant if sec represents an invalid number sequence. Get more digits if sequence represents an incomplete number of sequence, or subscriber rule if sequence lookup works. Sec represent a valid subscriber models. Okay, so we have another example. If I have time after, I think I will try to re-implement this code in modern Erlang. But I also think we have some issue because this syntax is weird. I don't know why we have. I think it's a typo or something like that. But it looked like some Prolog syntax there. So I don't know. Lookup works by recursively stepping down a 10-way tree. Each node of the tree contains either a subtree, which is also a 10-way tree, which indicates that more information is required, or a leaf. Leaves contains either nil, which indicates a vacant number, or a structure subscriber row, indicating a valid subscriber number. That's quite interesting, because this syntax is directly from Prolog. When you are defining a data structure in Prolog, for example with SWI Prolog, you need to define, to put this kind of symbol before it. this one. I mean, maybe it's a record. I don't remember. But I already have seen this syntax before. It's interesting. It's like a record. Implementation. An interpreter for the language we have described has been written in 6.2 Prolog and ported to a number of different machines, VAX, Sun, and PC. The entire system consists of some 4,300 lines of prologues. This line couldn't include all comments, blank lines found in the source code files. In terms of line of code, the major part of the program are as follows. So, for the tokenizer, you have 262 lines, for the parser 626, module system you have 394, for the interpreter you have 1256, and for the hardware interface you have the 605 lines of code. The remainder providing pretty printing facilities, debugging, top loop, and so on. This system provides the basic Erlang kernel. On top of this, we had some 4,000 lines of Erlang, which provide basic operating system facilities. It is a measure of the power of the producing system and of Prolog that the entire system has been totally rewritten on several occasions. This has been caused by major changes to the language or to the underlying philosophy of the operating system. For example, a change from asynchronous to synchronous communication will occasion a major rewrite. The time for such a rewrite is of the order of 2 weeks. That's crazy. The telephony software development cycle. Prototyping telephony software follows a cycle similar to the language development cycle. Ideas about an architectures, prototype of the architecture, verification of architecture on telephony hardware. However, this cycle may, of course, have an inner loop in which we test the implementation or indeed the specification of particular features. Since many of our new ideas about Erlang have emerged while prototyping architectures, the software development cycle and the language development cycle are interrelated and should really not be seen as separate activities. When this process has finally converged, the result is a design of a software architecture. This design can then be used as specification as for a more conventional type of project. The great advantage is that all the key design issues can be experimentally tested in the prototype. Prototype environment. A language and a way of executing programs in that language are of little use unless they are embedded in a suitable environment for testing and running experimental programs. Earlier experiments, we found that simply simulating telephony hardware was insufficient. The introduction of real telephony hardware introduces a necessary complication to test program. In order to work, this program must not only be a logically correct implementation of the specification, but they must also generate the correct sequences of hardware command and be able to receive the messages actually sent by the hardware. Using real telephony hardware to force this experimental program to be complete, the feature being prototyped must work in reality. must not only be a logically correct implementation of the specification, but they must also generate the correct sequences of hardware command. This part is great. Our telephony hardware consists of hardware from the Ericsson MD110PABX system, line interface modules interconnected by a group switch are connected to Sun workstation. We have modified the limb in such a way that all messages from hardware units are sent to the Sun, and the Suns can send messages which directly control the hardware unit in the limbs. In this way, the Suns themselves become the processor controlling the system, and we avoid the problem of cross-compilation, downloading of compiled code, remote debugging, and so on, which would be the result of having different host and target environments. We use the X Windows system at the front end to our system on the Sun, and have chosen Sixtus Prolog as the most suitable Prolog system. No discussion of our environment can be complete without mentioning the ever valuable GNU Emacs editor. More than just an editor, rather a way of life. So, even in 1989, the Emacs editor is probably the main editor for all Erlang code. That's crazy. The software of the system, and in particular the telephony software, is always in a state of change, several people working on it at the same time. We therefore use the revision control system to keep track of current version. Quite old. It was, if you, RCS was the ancestor of CVS, so quite old. The workstation used for prototyping works are deliberately placed very close to the telephony hardware. In this way, designers of, for example, features module can not only test their program by simulation but also test it in the real hardware world without leaving their chairs. In fact, there is little difference between the test environments when real and simulated hardware is used. Using real hardware enables the designer to experience the feel of the services they are creating and prevents them from slavishly following unrealistic specification. Erlang is about reality, real world, and here we have an example of what does it mean. When you are using Erlang and when people were developing Erlang, they were really close of the problem. You know, this is not like you are in some place and you are designing something from some weird specification and obscure requirements. Here, they are developing directly in the same environment that their software will work in. So when they deploy something, and if their workstation servers are just crashing, for example, they need to fix them manually, and they don't want to do that. They want to create some kind of automation, some script, some procedure. That's the way we are developing real stuff. Really. Experiences. The original ideas behind Erlang have been shown to be sound, but the language itself bears little resemblance to the first draft. It is difficult to see how the present language could have been obtained without prototyping. Previously, the software architecture of telecommunication system has been designed by relying on experience from previous systems. It is this word is, yeah, not surprising that the first generation of SPC system had a structure which resembled the electromechanical exchanges which were their predecessor. Other constraints on early systems were the physical limitation, which memory cost and limited processor power imposed. Our system has enabled us to experiment with the software architecture of telecommunication system in a manner which has previously not been possible. It has been possible to critically examine the trade-off which system designer must make between the complexity of different parts of the system. If, for example, one structures the application architecture around a naive port implementation, it becomes very difficult to add more advanced features, such as third-party services, operator intrusion, and so on. A restructuring of the system, which increases the complexity of pods, results in an easier introduction of such features. Another complex problem, which is very difficult to examine without resorting to prototyping, is the interaction between features. It is very easy to write a specification of a feature per se. It is only when it comes to implementations that the more complex cases of interaction between features become apparent. Perhaps the most important part of the definition of a system architecture is the definition of the semantic of the major interfaces in the system. We have found that prototyping allows these interfaces to evolve in a natural manner. One can try several possible solutions since the amount of work required to test each solution is relatively small. Once the best solution has evolved, the prototype becomes the definition of the interfaces. That's crazy because this kind of TDD, test-driven development, you are prototyping something, you are creating something from scratch. You have a blank page and you do a lot of testing, you are breaking stuff, you are dealing with all the reality you have around you, and one day you find the right syntax, the right tool to do something, and there where you actually those guys were just using TDD and just break and create and recreate and re-break, and that's nice. Abstraction play a very important role in the design of complex systems. At the highest level of telecommunication system, it is of great value if software designers can use simple and succinct abstraction which are related to telephony and not to the internal structure of the system. It is particularly important that this abstraction are totally independent of the hardware used. For example, some switches can themselves send tones to the channel connected to them. Others require that several tone sender units are used. An abstraction which encompasses the concept of a tone sender would then be inappropriate in a system in which tone senders are not used. However, an abstraction which seems clear and simple on paper may be extremely difficult to implement in practice. A prototype soon reveals how easy or difficult it would be implement a proposed abstraction in the real world. Crazy stuff. The conclusion. The idea behind rapid prototyping is that we should be able to test our ideas in the small. This is often interpreted to mean quick and dirty hacking. Nothing could be further from the truth. Rapid prototyping is possible by using modern languages and tools, designing and testing a subset of the total program. We have found that the use of Fixtus Prolog on Sun to be a very suitable tool. Using real telephony hardware is necessary when prototyping telecommunication software. Rapid prototyping allows experimentation with system architectures and enables the definition of system interfaces and abstraction. We have definitively the definition of TDD. It's, yeah, just break stuff, and when you are okay with the solution, and if you think it's an elegant solution, just use it. I think this is a way to do a really good software. Future work. Experience with the prototype has identified several interesting areas for future work. Analysis of various Erlang programs and observation of the programming process itself has given us several insights into the kind of mistakes that are typically made when programming telephony application. Some of these mistakes can be removed by changing the semantic of Erlang so that programs with such errors cannot be written. We also hope to provide programs that perform static analysis of Erlang code for common classes of error. So dialyzer, and type checker and so on have been not created, but the idea of those tools were already present in Erlang at its beginning. Another hope is that we can make Erlang more declarative. One way of doing this would be by removing strict sequencing from the language. The code could then express what had to be done but not the order. An inference system given this code as an input could compute the order in which the operation had to be performed. We will integrate our prototyping environment into a modern programming support environment. The raw Prolog interface we use today needs improvement, as do our method for source code control. The authors would like to thank the members of the computer science laboratory and in particular the members of the Dunder project group for their help and support in this project. Okay, that's really great. That was a really great paper. It's sad we can't use Proctus, but I think just for the syntax, I don't remember the name of this thing. I will check that just after. But anyway, this paper is great, and I found there a lot of answers, and some of them, some confirmation about the name. For example, Erlang is not from the Ericsson language, but it's about Agner Erlang. So we have the proof here. And if someone told you, Erlang is Ericsson language, no, it's about the mathematician, and it's a good way to express this language because this reference is about stochastic processes in statistical equilibrium. So Erlang I think it's Erlang formula. Please, Wikipedia. That's really interesting. So this is the name of Erlang. This is why Erlang is called Erlang. And it fits totally with the language, statistical probability distribution, unit of communication. It's great. Okay, so I think I don't know what time is it, but 1 hour. I think it's great. Maybe if I have 10 or 20 minutes more, I will try to do something to re-implement those code here. But because the syntax is a bit different, not sure if I will be able to do that. In particular, these things here. I would like to check about the Prolog syntax, because I think this is a record, and in Erlang we can express that like this. So for example, you are defining a new record. I think it's something like that. No, it's not RL, it's RT. And so now you can express something like that. And woo, it's now containing the test value. And I think that's the ID. So we have the subscriber, and we just set a new value. But I'm not sure, to be honest with you, I'm not sure. I need to check that. But that's a great paper and a beautiful one. So it's really nice to have started this new session with that. So anyway, 1 hour. I think I will stop there. If you have question or something like that, just ask them. I don't know if I have access to Twitch. Okay, there is no message on Twitch. And here. Okay, so I think the music was a bit loud. I hope everything was fine, but yeah. So see you later, and thank you to be there. And it was the first live session about papers. Maybe the next time I will just remove the music, and well, we'll see. So anyway, have a great weekend and see you next week. Bye.